See the difference? So that's dr dt. And how are those related to the velocities of 1 and 2? Well, very simple, right? We have v1. You just differentiate this. The mass is constant, so this gives you a linear relation between the velocities. R is equal to big V minus m2 over m1 plus m2, little v, and v2 is equal to big V plus m1 over m1 plus m2, little v. Then, all right, well that's pretty awesome. And then you can calculate the kinetic energy. Well, I'll just go ahead and calculate the Lagrangian. The Lagrangian is what? Well, it's 1/2 m v1 dot v1. I should say m1, right? Plus 1/2 m2 v2 dot v2. So there's the kinetic energy for the first mass plus the kinetic energy for the second mass, and then minus u, which is just a function of, r. All right. By assumption, it's a central force. Okay, and then we work it out. So what's v1 dot v1? You see what you got? You got yourself a v dot v, big V dot big V, minus 2 m2 over m1 plus m2, big V dot little v, plus m2 over m1 plus m2, quantity squared, little v dot little v, plus 1/2 m2, and then again I get big V dot big V, this time plus 2 m1 over m1 plus m2, v dot v, big V dot little v, plus m1 over m1 plus m2 quantity squared, v dot v. So what happens? Yeah, we have 1/2 m1 plus m2 times, let's say, big V squared, right? Big V squared would be big V dot big V dot, right? It's the velocity of the center of mass coordinate squared. Then what? Yeah, plus 1/2. Looks like I've got a let's say m1 m2 squared plus m2 m1 squared, all divided by m1 plus m2 quantity squared, right? Times little v squared. That's the other terms, right? And you say the mixed terms cancel? Well, that would be beautiful. Does that happen? Let's see here. I've got a minus m1 m2 over m1 plus m2, and over here I've got a m. Hey, awesome. That's why center of mass coordinates, why, by the way, are what they are, which is worth looking at. Ka-chunk. Ka-chunk. Yeah. So this is really, really nice. Does this simplify? So this is 1/2 big M, big V squared. And of course, you guys don't let me get away with that, minus u of r, right? You see, if you look at that, you can factor out m1 plus, I think you can factor out m1, m2 times m1 plus m2. So there's a factor of m1 plus m2 that cancels, and you're just left with plus 1/2 mu little v squared, where big M is the total mass, it's m1 plus m2, and little mu is the so-called reduced mass. It's the product of m1 and m2 divided by m1 plus m2. Yes, Joe? No, they're there. We need them because otherwise it's not the kinetic energy. Yeah.
It just looks like you're adding two halves.
Well, but I'm not adding those. They're never. I mean, they're added, but they're not combined. So a typical application of this, you guys, would be something like m1 is equal to the mass of the sun, right? And m2 is the mass of the Earth. All right? In that case, the reduced mass is what? So the mass of the Earth is essentially nothing compared to the sun, and so you just get mass of the Earth, right? So the reduced mass becomes the mass of the satellite if the central gravitating object is very large in mass, comparatively speaking. And how about the center of mass? What's R in this case? So if you look at it, if the mass of the sun is huge, let's see how you can say this. Where's the center of mass? It's basically R1. It's where the sun is. So in freshman physics, we set R1 equals to 0, and we pretend the sun doesn't move. And that's a pretty good approximation, right? But I make no such assumption here in this derivation. Okay. All right, so going forward, if I may, if I have time, if you don't mind, guys, I'm going to finish this up with the projector, as to not keep you over. This may offend Paul. I'm not sure. So how do you guys like taking classes with Crazy Paul? How's it feel? For me, it was a very enjoyable experience. He always added a certain extra element to any class.
It'd be interesting to see his views on 7 as a variable.
What's his view on 7 as a variable? I don't know, but I'm quite sure he would have engaged you in conversation about that. And I would have walked away from it, being happy that you distracted Crazy Paul, allowing me to work. Crazy Paul viewed one of his chief missions in life is to keep me, what's that? Oh, yay! This calculation is not cowardly, so it's good. This is the, if you break the V into big X, big Y, big Z, and break the little r into, say, X, Y, Z, then that would be the Lagrangian mx dot squared, y dot squared, z dot squared, right? Plus 1/2 the reduced mass. And so if you look at the Euler-Lagrange equations for the center of mass coordinates, it's really, really simple. They're just straight up mx double dot, y double dot, z double dot equal to 0. In other words, the motion along the center of mass is constant rectilinear motion, just constant velocity motion. So if you think about the Earth-Sun system, it's basically just saying that the center of mass of the Earth and the Sun just kind of goes throughout the universe just at constant velocity, whichever way it's going, right? So obviously this model neglects, first of all, it neglects all the other planets, which isn't very accurate. But also it neglects things like the pull of the Andromeda galaxy or whatever, all right, which is probably more realistic than neglecting, say, Jupiter. So that's easy. So essentially, then we're left with the more interesting problem of how does the center of mass, how does how does this coordinate evolve with time? So calculus 3 shows you that the motion is planar, because if you look at the force of gravity crossed with r, you get 0 because it's, well, anyway, a little calculus 3 argument gives you that the motion is planar. I don't have time for that today. So we can assume that little r is x dot squared plus y dot squared. And then, of course, the way to do that properly is to use polar coordinates. 1/2 mu r dot squared plus r squared theta dot squared. So you look at the Euler-Lagrange equations, and you get mu r double dot is equal to minus partial u partial r, plus mu r theta dot squared, and then you get mu r squared theta dot squared is equal to 0. This shows that the angular momentum is conserved. So you can say L is equal to mu r squared theta dot, and then you go back to the radial equation, which is this, mu r double dot minus partial u partial r plus mu r L squared over that. You can, so here's one of your homework problems. I ask you to show energy is conserved. The way to do that, guys, is to take the Euler-Lagrange equation and multiply by the velocity. For example, if I had mx double dot plus kx equals to 0, those would be the Euler-Lagrange equations from like a spring mass system. If I multiply this by x dot, oh, excuse me, not kx. Look at it as plus du dx is what we'd have, all right? So the chain rule then allows me to say that this 1/2 m x dot squared plus u ddt, because I'm using like dx dt times du dx is equal to du dt to pull out a derivative there. And then this is, by the chain rule, the derivative of that. So if you multiply the equations of motion by the velocity, you can get energy conservation for a conservative system. Sorry, I thought I should say that about your homework. Let me get back on track here. So where were we? That's the radial equation. Okay, so then you can multiply this by, well, excuse me, you just pull out the DDR if you look at that, right? This is the derivative of u. And then if you look at this, that's L squared over 2 mu r squared. If we differentiate that with respect to r, I'll get a minus 2 over r cubed, which is what I have here. But the 2 cancel. You guys see that step? It's just calculus. Guys with me? So I just rewrote the radial equation a little bit. I brought everything to one side, and then I multiply by the velocity. Multiply by dr dt. When I do that, I can then do, this is r dot times r double dot, which if you differentiate this, you'll get back to that because you get 2 r dot r double dot, and the half and the 2 cancels. Yeah. And then over here, you see that's, I have, this changes the r derivative on u to a t derivative by chain rule, and likewise for that piece. So this is energy, which is also a conserved quantity. So we're 2 conserved quantities for the central force problem, angular momentum, and this energy. And so the energy is that. This gives you what's called an effective potential. It's like, here's the gravitational potential, and then there's this other piece, which is, and so you can analyze it as if it was a potential, even though, of course, the L squared over 2 mu r squared is essentially a coordinate effect. So basically, you got to solve these 2 equations here, d theta dt and dr dt equal to blah. It turns out that there's this sneaky change of variables you can make. Instead of solving it for r, you solve it for, let's see here, where did I go? You solve it for u. Let u equal 1 over r. When you make this substitution and work it out, the radial equation becomes something really, really simple, the so-called orbital equation. The orbital equation down there is underlined. This is just straightforward substitution stuff. Any differential equation student ought to be able to hack it. I've made it homework in differential equations before. So you get second derivative of 1 over r plus 1 over r. So you see, Nathan, this is essentially a constant coefficient differential equation in 1 over r. But then there's this like, But what happens when the force is reciprocal in the radius? Squared. See what happens? R squareds cancel. You're back to the, again, the standard cosine sine solution for 1 over the radius. And so in the case that's most interesting to physics, the reciprocal law, you can solve this equation using constant coefficient ordinary differential equations with a forcing term. and out pops this equation. R is equal to 1 over some constant cosine of theta. And this is exactly the equation for a conic section in polar coordinates. It's in either an ellipse, a hyperbola, or parabola, depending on the choices of the constants there. And that is how you derive that orbital motion is either hyperbolic, parabolic, or an elliptical thing in some plane. And I know I hurried a little bit, but you see if I spend an hour going carefully through this, it would be a pretty complete derivation. And that is the power of Lagrangian mechanics in a nutshell. It is so much better for solving problems than what we have to teach you in the first course. And there you go. That's the difference between being a physics major and being a science major. You get to know these secret things, so you can solve problems that no one else can dream